Okay, one more application of geometric series. I call this living off of savings. Very common circumstance people find themselves in. Doug and Pat has saved $500,000 for their retirement, and they're wondering if it's enough. Can they retire tomorrow? They plan to live for another 25 years, withdrawing the same amount each year, and their money will earn 3.8% annually. How much will their yearly withdrawals be, assuming that they'll have no money remaining in the account after 25 years? So you can see that um, if they had this money stuffed under the mattress and they wanted to pull out the same amount for 25 years, you could see that it's just going to be $20,000. But you would see that it's going to be 500,000 divided into 25 parts. Each part $20,000. Now, can they live off of $20,000 a year? I'm not sure. That's up to Doug and Pat. But if they stuffed it under their mattress, they would have $20,000 a year for 25 years. Now, if their money is earning interest along the way, 3.8%, then they're going to be able to make a little bit more than $20,000 per year. Or they're going to be able to withdraw a little bit more than $20,000 a year. So we already have an idea of how big our number is. It's going to be something bigger than 20,000. How much bigger is the question? And in order to understand that number, or to get that number, you have to do a geometric series. Okay, so let's do that. Let's start by defining some variables. We're going to let B sub n equal the balance in the account after n withdrawals. Okay, notice I don't say years. I like to think about these in terms of the actions that are happening. And then we need to say let x equal the annual withdrawal amount. We don't know that number. We're trying to figure out that number. That's the number $20,000, but something bigger than that. Okay, so let's write out the first few terms of this geometric series. We're going to say after 0 withdrawals, there's $500,000 in the account. Okay, let's say they retire tomorrow and they have no more paychecks and they need the money right away. So B sub 1 is going to be $500,000 minus X. Okay, and that amount of money is going to sit in the bank for a year. So that's going to earn 1.038% interest. Okay, so that's the amount, I guess you could say, right before the second withdrawal, or you could say after the first withdrawal, but that money is going to stay the same amount, 500,000 minus X, for the whole year. Okay, and then B sub 2, wait, I realize that there's lots of ways of going about this. This is just the way I think about it. You can set up maybe B sub 1 would just be 500,000 minus X, and B sub 2 would be counting up the interest. But it doesn't really matter. But what does matter is that we have withdrawal before interest. I like to think of this as sort of they retire tomorrow and they need the money right then, and then some amount less than $500,000 is actually what earns interest for the year. That's just the way I think about it. Others might think differently, but that's how I'm going to set this one up. Okay, before I go any further, I want to simplify this. This is 500,000. Just going to distribute this times 1.038 minus x times 1.038. Okay, after the second withdrawal, I've got this amount of money over here sitting in the bank. So that's the amount from which I subtract another withdrawal. Okay, so this is the amount of money in the bank, and this is what I subtracted. And then during that whole year, after that withdrawal, the money earns interest, 3.8%. Okay, and this, I'm going to distribute this 1.038 as well. That's going to make 1.038 squared minus x times 1.038 squared minus x times 1.038. Okay, and I think you could see the pattern coming as they normally do with these geometric series. that if I skip down, now I want to go to B sub 25 because I need to make 25 years. So that's 25 withdrawals. In order to pay for 25 years, I need 25 withdrawals. And that's going to be 500,000. And you can see that the subscript is 2 and the exponent is 2. So in this one's going to be the subscript 25 and the exponent of 25. This one also has an exponent of 25. And this one's going to be 24. And it's going to go all the way down to x times 1.038. And I know it seems a little weird to have that last withdrawal with interest on the end of it, but I want to stay consistent with the geometric series more than I want to make the reality reflected, because in truth, it makes sense that to get down to $0, the last thing that should happen would be a spend. But this is just the way that the geometric series is playing itself out. And if you are getting interest on $0, then it doesn't really affect the balance. It's just going to be an extra multiplier. So it doesn't really matter at the end there. Okay, so what do I want the balance in the account to be after 25 withdrawals? $0. And I want to identify that I have a geometric series on the right side of the equation. Not the entire right side of the equation, but just right here is the geometric series. Okay, and I just enclosed the geometric series in parentheses with a subtraction sign outside of it, which means I change all of these minus signs into plus signs. So instead of subtracting each one, I'm going to subtract the quantity of them added together. Not only that, I'm going to identify this one as the first term of the geometric series. I'm going to identify this one as the 25th term in the geometric series. Okay, so if I'm counting from an exponent of 1 up to an exponent of 25, I've got 25 things. Okay, so this part doesn't change. This is just 500,000 times 1.038 to the 25th. And then I've got the geometric series, which I can express as a fraction. First term is x times 1.038. And then I do 1 minus the common ratio, 1.038 to the n, 25 terms, all over 1 minus 1.038. And my goal here is to solve for x. So I have to do some fancy footwork here. If these two quantities subtract to be 0, then they better be equal. So I'm going to, I'll do a step by step here. I just want to get too fast. 500,000 times 1.038 to the 25th. And then I'm going to set this equal to, and I'm just going to pull the x apart. This is x times 1.038 times 1 minus 1.038 to 25th, all over 1 minus 1.038. And I did that. This is x times this quantity. I pulled the x off of the numerator just so you could see that it's like a coefficient, or it's like x times 6. And I'm gonna divide this quantity to the other side, or divide both sides by it, or best said is I'm gonna multiply by the reciprocal of this factor right here. So I've got 500,000 times 1.038 to the 25th. The denominator comes to the numerator, 1 minus 1.038. And the numerator goes to the denominator over here, 1.038 times 1 minus 1.038 to the 25th. And that's what equals x. Before I pick up my calculator, I'm going to recognize that I've got a common factor here. That is going to divide with one of these, which is going to make 24 of these. That's going to save me a little typing. Okay, so I pick up my trusty calculator, and I'm ready to type this in. Hopefully this number will be something bigger than 20,000. So 500,000 times 1.038 raised to the 24th. Okay, I realize I don't need that parenthesis right there. I don't like his parentheses. I try to get them out of there if I don't need them. I do need to subtract this quantity. 1 minus 1.038. That's a subtracted quantity, so I need that to be multiplied. Let's just see here. I don't need this, but I'm going to put it in there just so I can see it better. Okay. And, the calculator knows the order of operations, so it knows to do the exponent before the multiplication. So I see a lot of students having a hard time with the parentheses because they don't trust that the calculator knows the order of operations, or they don't trust themselves to know the order of operations. But it's going to do the exponent first, and then it's going to go left to right multiplication division. So it's going to do this next, and then it's going to multiply what's inside the parentheses next. So I'm in good shape. And I just need to divide by the subtracted quantity in the denominator, 1 minus 1.038 raised to the 25th power. Okay, and this should be, yeah, a little bit more than $20,000. Quite a lot more, actually. $30,185.91. 30,000, I've already forgotten. 185.91. 185.91. Okay, so you can see by putting the money in the bank instead of shoving it in their mattress, Doug and Pat are able to have $10,000 more per year, roughly, over those 25 years, which means they've basically earned about $250,000 in interest. Okay, so that's important. So they have $500,000, okay, but they're actually spending, let's multiply this number by 25. Okay, so they started with $500,000 and they actually spent $754,000. Let me just make that clear. Doug and Pat used $500,000, or I should say retired with, right? Retired with $500,000, but can spend, or can spend 754,647. 754,647 and change. Yeah, so that's good. So that's quite a deal. $254,000 extra by putting it in the bank instead of putting it in your mattress. That's a 50% bonus. Okay, so that's like add 50% of your retirement to your account coupon, which would be great. So it's a 50% bonus. That's a big deal. Okay, that's a lot of money to be having the bank supply for you. And I guess if you look back over this problem, you can see that 25 years is really the key. 25 years is a long time, and you expect good returns and big deals off of your investments in 25 years. 3.8% is also a variable that you could play with. If obviously if the interest rates were higher and a good economy, and then this $30,000 number would go up, and they'd actually have more money to spend. But I think 3.8% is a pretty prudent, not too risky for an old person, and you can see that it pays to put your money in the bank and try to live off of it in installments. Now, the final question, I guess, is can Doug and Pat live comfortably on $30,000 a year? Maybe they can't. Maybe they have to supplement their income in some other way. Maybe they have to get part-time jobs or something. That's not the concern here. We're just thinking about how this geometric series works. Okay, hope that's clear.